All right, so this is, I believe, Vectors Lesson 4. So today we're going to focus in on some applications to force and velocity. So those of you taking physics, this will look all very familiar. But like I said, this is not going to be the crux of this course, so we're not going to spend too much time on it. So first of all, let's introduce some vocabulary. So let's say I've got somebody applying a force to an object, in this case here, this donkey. So that would cause motion in the direction of the force, but of course the donkey might also be exerting a force in the other direction, all right? So the force that it takes to counteract another force is what we call the equivalent force, okay? And the equivalent force is essentially the opposite of the net force on an object. Now here, if there's just one force on an object, then the equivalent force would just be, you take that force, you take the opposite direction, and there you go. There's the equivalent force, okay? But of course, sometimes you might have more than one force on an object. All right, so it could be that this is made up of the sum of a couple of forces. Okay, so let's say we've got two forces acting on this object. Okay, so if you want to find the equivalent force, in other words, the force that's needed to counteract them, well, first you would add up all the forces. Okay, and all the forces acting on an object is what we call the net force, and then the equivalent would just be the force that's equal and opposite to this net force. All right. So we've brought in now a couple of things here. So first, this idea of the net force, okay, or if we use the term that we've been using with regards to vectors, the resultant force, so they essentially mean the same thing, is just going to be the sum of all forces acting on an object, and the equivalent force is the force that counteracts that net force, okay, if you want to create what's called an equilibrium, meaning where there is, at least in this point here, we'll call it no motion. Again, for those of you who are taking physics would understand that being in an equilibrium doesn't necessarily mean that you're not moving, just means that the net forces are zero, okay? So speaking of being in an equilibrium, here's another example where you have an object that's hanging from two strings. It's an equilibrium, okay? Now in this case here, let's take a look at all the forces that are acting on the object, okay? Well, you've got the force of gravity pulling this thing downwards. Okay, well, let's make this a little bigger there. Okay, then you've got the forces that are acting on in the direction of each string. Oh, not sure why that's not happening. Let's try that again. Okay, so you've got a force going in the direction of the string and then a force going in the direction of that other string. So these are all the forces that are acting on this object, but the object's not moving. So who can tell me what is special about all these forces? What relationship do all these forces have?
They add up to zero.
Okay, they're going to add up to zero. The net force has to be equal to zero. Okay, so I'm going to talk about the idea of considering this with respect to components a little later on. Okay, but like I think I've mentioned here, while you're perfectly welcome to solve problems this way, I'm just going to stick with one way of solving the problems throughout. Okay, that's not going to involve that. So the idea here is this diagram is what I'm going to call a situational diagram. In physics probably call this free body diagram, but it gives you a sense of what's happening in this particular situation. I've got my object and I'm indicating the three forces that are acting on it. But in order to solve a problem like this, what I want to do is I want to create a force diagram, meaning I want to see what happens when I combine all these forces to determine the net force. Okay, so if I'm going to draw this, well, I've got the force of gravity going downwards. That's nice and easy, nothing special there. Okay. But then I've got the two other forces acting on the object. So say I take this force here, so let's add it tip to tail. So it's going to look something like this. Then what's going to be special about that other force? Like, I don't have any information. I have no information about direction. I have no information about magnitude here. But what do I know for sure when drawing this third force?
It has to touch the tail of the gravity vector.
There you go, is that the net force we said has to be equal to 0 because this object is not moving. So I know that this third force, when I place it tip to tail to the second one, is going to have to go back to the tail of the original one. Because what does this mean? It means that when I add all three forces together, I get back to where I started from, meaning that the resultant vector, or in this case here, the net force, is equal to 0. So this is where we realize that when you have a net force equal to 0, the force diagram will always result in a closed shape. In this case here, that closed shape is a triangle because I have three forces. If I had four forces that were in equilibrium, then there would be some sort of quadrilateral. All right. Now, essentially, the types of problems we're going to solve won't ever involve more than three forces. So this is why, if I'm only going to be creating triangles, instead of coming up with some new way of solving these types of problems, I'm just going to be using good old trigonometry to solve these problems, like we have so far in the stuff we've done previously. Okay, so when you're dealing with several forces, okay, you could draw a diagram that describes a situation, the direction, and getting a sense of the magnitude of these forces. But in order to solve the problem is to take these forces and draw a force diagram or vector diagram that, in this case here, because the net force is 0, creates a closed shape. All right. So the last thing I'm going to introduce right now, actually, no, before I do that, as I said, I was going to talk a bit about this idea of components. Now, sometimes, and we'll see in one of our questions, it's useful for us to talk about forces as being broken up into a sum of other forces. In this case here, you notice that I've taken this vector u and I've written it as a sum, because look, tip to tail, of two forces. Now, what's special about these two forces is that they're perpendicular to each other, and one's horizontal and one's vertical. So we're going to see that one of the examples is somebody pulling a toboggan, but they're pulling at an angle. And if I want to determine the force that's producing the motion in the horizontal direction, well, I'd only be interested in this force here. Okay, so this idea of breaking up a force into two what we call component forces. Okay, now you can see that because I've chosen to break them up as perpendicular forces, you're going to be able to use good old right angle trigonometry. Okay, however, we're not going to assume that we're always breaking things up in terms of horizontal and vertical forces. We're going to see an example where we have a vector that's going downwards, and it's probably going to be useful to break this up still in terms of two perpendicular forces, okay, but not vertical and horizontal. Okay, so you can break up a force, okay, and you see here, okay, well, I should have drawn a little better. Let's draw it a little nicer there. There we go. There's this force here that's being broken up into two perpendicular forces, the sum of two perpendicular forces, but not necessarily vertical or horizontal. Okay, now, for those of you who might not have taken physics, I'm not going to solve problems this way, but just to give you a sense, if you hear people talking about this idea of components, another way of solving these problems without using triangles, or at least where you're adding the forces to get triangles, is normally, if I want to add two forces, well, I place them tip to tail, and there you go, I find the resultant. Well, what's often done in physics, and this is certainly very useful when you're dealing with several forces, is to break up each of the forces into components, into vertical and horizontal components. So now when you look at the resultant, you realize, hey, that's the same as taking the horizontal component of the first and adding the horizontal component of the second. And look what that gives you. It gives you the horizontal component of the resultant vector. And then you do the same thing with the vertical components. I take the vertical component of the first and I add it, a little off there, to the vertical component of the second. And that gives me the vertical component of my resultant vector. And this is how they solve all of these problems, is by breaking everything up into these perpendicular components. So this is just an alternative way to solve these problems. Not the one I'm going to use, but just to make you aware of this alternate way of solving these problems. Okay, that looks a little better. All right, so the last thing now that I want to talk about before we go over the notes and I give you some time to work on the problems is with velocity problems. Again, this idea of a resultant velocity. So we already talked about resultant forces. We add all the forces together. Well, if I have a plane that's flying at 200 kilometers per hour in completely still air, so no wind today, okay, well, a person on the ground, okay, will be seeing this, and it will be seeing they'll be seeing the speed of the plane as 200 kilometers an hour. But let's say the next day, there's now a wind, okay? Well, the plane is still heading in the east direction, say, at 200 kilometers an hour, but this wind is gonna naturally make it go faster. So how do we determine what the resultant velocity is? Well, I would take the velocity of the plane, and then here, it looks like the wind is blowing in the same direction as the plane is moving, and you just add the velocity of the wind, and you get this resultant velocity. So somebody who's on the ground, what they see is the plane traveling at this increased velocity. All right, this is why we call the resultant velocity the ground velocity. So what someone on the ground would perceive as the velocity of the plane. All right, but of course, the wind's not always blowing in the same direction, might be blowing, say, at an angle, okay? So if the velocity of the wind, say, blows at an angle, well, not surprisingly, to find this resultant or ground velocity, we're just gonna add the two vectors together. And this is going to be the actual motion of the plane, what somebody on the ground would perceive as the motion of the plane. Okay, so a resultant velocity has, we use the term ground velocity, and that's the idea. And this would be similar to somebody standing on the edge of a river and watching a boat moving. Okay, it would perceive the resultant velocity, meaning the motion of the boat plus the motion of the, say, the wind or the current. All right, so let's take a look at the notes here, see what we got. So, sum of all forces acting on object, resultant or net force. Okay, object will remain in a state of equilibrium if the net force on the object is equal to 0. So all the forces add up to 0. Now again, in terms of what we're solving, this is going to mean that the object is not moving, okay? But that's not the only state of equilibrium that exists, okay? And then this idea of the equilibrium force is the force required to keep an object in a state of equilibrium. So you just add up all the forces, you get the net force, and it's just going to be the one that's in the opposite direction, all right? Now, a couple of things. Very often, we don't give you directly the force due to gravity. We often give you the mass of an object. Okay, well, as long as we're near the surface of the Earth, then we'll assume that even if we're in the air, we're still near the surface of the Earth. Okay, there's a nice formula that just gives you the force due to gravity. It's just 9.8 times the mass of the object. 9.8 being the acceleration due to gravity. Okay, so if they give you a mass of 10 kilograms, you know that the force due to gravity is just 9.8 times 10 kilograms. Okay, we talked about this idea that if I add three forces together that are in equilibrium and I add them tip to tail, I get a closed triangle. Okay, if it was 4 forces, 5 forces, 6 forces, I'd just get some closed polygon. All right. Now here, if three forces are in equilibrium, then the magnitude of one force cannot be more than the sum of the other two forces. Well, let's take this example here. Okay, let's say I take the longest force. We can see clearly that this is going to have to be shorter than the sum of those two other forces. Can anybody tell me what the sort of upper end, what's the largest that the largest force could possibly be? Who could tell me what the, the biggest possible force you could have for the longest force when you've got three forces acting together? Okay, so we have an answer. There you go, the sum of the two. Because if you were to place these two one after the other, so let's maybe go back here. Okay, if I place, here, if I've got two forces and there's the third, well, the best I could do is have the two forces one after the other, and then the third force, remember we're working in equilibrium, okay? To create the equilibrium, there you go. That's the biggest possible I could have, is that the longest force is the sum of the lengths of the other two forces. All right, let's go back. Okay, we can take a force and break it up into perpendicular components. Of course, you can break it up into non-perpendicular components, but that's just not something we're going to be seeing here. And this could be horizontal, vertical, or any combination. Okay, and lastly, this idea of ground velocity is essentially another word for resultant velocity. So when you add all of the velocities that are acting on an object, that resultant velocity is called the ground velocity. So again, examples, if you're looking at something in the air, it's going to be the velocity according to the instruments of the, say, plane, so what we call the air velocity, and then of course you're incorporating the wind velocity. Okay, if you're looking at a boat from the shore, it's likely going to be the velocity in still water, so meaning what are they actually rowing at, plus whatever the velocity of the current is. Okay, any questions on any of this before we talk about what you're going to work on? Okay, so what I'd like you to do is, and I'll just bring them all up so that you can see them, is because I can't stay past 10, what I'm going to do is I'm going to give you about 15 minutes to start these problems off, okay? So I don't want you to worry so much about solving the whole thing, because the actual solving of it is just a bunch of trigonometry. What I want you to worry about is to try to draw a diagram and just start off the problem. All right. So you got these 5 questions. I'll just leave them on here. No need to write them out. Get a piece of paper and work on these problems and try to set it up. What would the diagram look like and how would you start finding that? Okay. So we're going to go till 9, but maybe just before 9:40. So I'll give you about, looks like 18, 19 minutes to work on these. And like I said, if you kind of get stuck on one, just move on. We will take them all up. But take some time to try to start every single one. So maybe give yourself 3 or 4 minutes for each one to get started. Okay, and I'll be around here for questions. Okay, so folks, we're back. So what I want to do is I've got the questions already written out. So it looks like there was a lesson question by email. Let's just came in now. Yeah, we're going to go over all this stuff now. Okay, so first thing I'm going to do here is I'm going to just draw the pictures and then we'll look at the solutions. Okay, so it says a boulder is being pulled by 2 people exerting forces of 40 and 60 newtons. attached at the same point at an angle of 25 degrees from each other. So we recognize this scenario that we're gonna be putting these vectors tail to tail because they give us the angle between the vectors. All right. So say this is my object, often represented by a point. Now, where the vectors lie really isn't important, because the only thing that's important is the angle between them in terms of doing a calculation. So I'm gonna choose to put one of my vectors horizontally. Okay, so say that's the 40 Newton vector, and then my other vector is going to be this one here, the 16 Newton vector, at an angle of 40 degrees. Now, if I'm looking for the equilibrant force, that means I want to know what force counteracts these two. So the first thing I have to do is calculate the net force, the resultant.
20.
Yep.
25 degrees from each other.
Oh, 25. Sorry. Thank you very much. I guess I was focused on that 40 there. There we go. 25 degrees. And so the first thing I'm going to do is find the resultant force. So how am I going to do that? Well, the easiest way to add this up is to take this force here and draw it tip to tail, and then I can draw my resultant force. Okay, but this is not going to be my answer. The answer is going to be the force that's equal and opposite to that one in the other direction. All right. So let's take a look at the solution here. Okay. So you see how I have my diagram started with my two forces. Looks like here I drew the 60 here, the 40 there. Doesn't matter because it's all commutative. All right. So once I have this triangle, a reminder that I need the angle inside the triangle, which is going to be one that's supplementary to the 25. So cosine law. Okay. In order to get direction, I again used cosine law. Okay, we talked about last time why I just go with cosine law all the time, because I'm working with one angle and two side lengths. So I just don't even want to think about ambiguous case. So I use the cosine law to find my angle. Okay, so now this is where, in terms of our direction description, we have to describe it relative to our vectors. So this little angle here is about 10 degrees, but of course I'm looking for the one that's in the opposite direction. So I just used my old supplementary angle formula, because if these two are opposites to each other, it means they form an angle of 180. So this angle here is just going to be 180 minus that small angle that I found of 9.95 degrees. Okay, so the way I chose to describe it is here. This is the 60 Newton vector. I'm not going towards the 40 Newton vector. I'm going away from the 40 Newton vector. And so that's how I'm describing my direction here. All right. So again, multiple forces acting on an object, you find the net force, and then for the equilibrant, if that's what they're looking for, is you're just taking the force that has the exact same magnitude as your net force, but in the opposite direction. All right. Any questions before I move on from this one here? Okay. So let's take a look at the next question. Okay. And this looks a lot like the one we talked about earlier. Okay, so you have a piñata held up by two strings. One string makes an angle of 30 degrees with the ceiling, the other makes an angle of 40, and they give you the mass of the piñata. Okay, so we've kind of drawn this diagram already, but let's go ahead and do it again. And here, because I have these multiple forces acting on the object, this is where I draw my situational diagram first. Now, while it's not explicitly told to us, I think it's reasonable to assume that the ceiling is a straight ceiling, so that's horizontal. So we've got our two strings that are attached, okay, and you've got two different angles. One is larger and one is smaller. Okay, so I'm not going to be accurate here, but I do want to show that one is larger and one is smaller. So this is a smaller one. I'll call this 30 and I'll call this 40. And then here I've got my object, okay? And let's figure out what the forces are acting on this object. Well, you have the force from one string that's going into one string, what we call the tension, then another force, tension going in from the other string, and then of course there's the force going down with respect to gravity. Okay, and what is special about these three forces? Well, this piñata is not moving. It looks like they haven't started hitting it yet, so it's not moving, meaning that the net force is going to be 0. Okay, so in order to solve the problem, let's draw our force diagram. Notice I always start with the easier one if I can. I know that this one just goes straight down, so I might as well start with that one there. Now, whether I do this force or that force first, well, it depends on, I guess, how much room I have on either side. Remember, the order doesn't matter. How I group them together doesn't matter. These are consequences of those vector properties. So that's why I can do this in any order. So I'll choose to do this one here. So I know I've got that force, but I'm going to want to solve a problem here. I'm going to need some numbers. So this is where I have to ask myself, how can I get some information about the direction of this vector? Can someone other than Enoch, Hisbon, or Andrea tell me how I can get some information about direction here? Let's try to get some other people in on here. Okay, so I see the alternate angles or the parallel line principle here. So I've got this horizontal line. If I think of drawing another horizontal line, I know that the two acute angles are going to be equal. So this is also 40. I might as well go and say this is also 30. So this here has to be 40 degrees. And so that angle there is going to be 50. Okay. I know that the third vector has to close off the triangle. So again, if I draw myself a little horizontal line here, I know that this has to be 30. And this now should give me some information because I know the force due to gravity. It's just going to be 9.8 times the mass of 10, so 98. Okay, and I know this is 50. Well, hey, if that's 40, that's 40. So that means this angle here is equal to 70. And of course, once I have two angles in a triangle, I have the third automatically. So 70 plus 50 is 120. So this is going to be 60 here. And now that I know all the angles in this triangle, can you tell me why this makes my life a little easier in terms of choosing what I'm going to use to solve this problem? What does the fact that I have all three angles allow me to not worry about anymore?
You can just use the sine law.
I can use the sine law without any worries. Isn't that nice? Okay, because I now know all the angles in this triangle. There's no guesswork here. So if we take a look at the solution, okay, so we got here's the diagram, my situational diagram, my force diagram. And now from here, what am I looking for? I'm looking for the tensions, okay? Now, we don't have to notice here how I don't give directions. Well, we don't have to because we know that it's going to be whatever the direction the string is tied to, okay? So what I'm looking for here is the magnitudes. By the way, notice I always have my magnitude symbols around here. If you just put T1 vector, no magnitude, and you give me this as an answer, that will result in some mark losses because it's the magnitude that I'm looking for. And here I can go ahead and use the sine law without any worries because I'm working with two angles and one side, and there's no ambiguity there. Okay. The only thing I'd maybe bring up here is you notice how I use the 98 in both cases. I don't use the 90.32 to calculate the next one. The idea is if you have an option to use an exact value, well, you should be using an exact value. Okay. So this is a very typical type of question, in terms of, sort of relatively straightforward equilibrium problem. Okay. Any questions on this before I move on? Okay. So I think for the next one, it's relatively straightforward. So we'll just take a look at it here because I'm looking at the time. I have to speed up a little bit here. So I drew my diagram. You know, I've got my force that's being applied 25 from the ground. So we assume again that the ground is horizontal. They don't particularly tell us, but we'll assume that's the case. And so what I'm looking for is determine the horizontal force that exerted on the toboggan, because it's this part of the force that's going to actually move the toboggan along the ground. And so when I draw my diagram and I split this up into a horizontal force and a vertical force, well, because I'm breaking it up into perpendicular forces, I can just use right-angle trigonometry. And so here, because the magnitude that I'm looking for is on the adjacent side, I can use cosine, okay? So while you're exerting a force of 70 degrees, 70 newtons, only 63 of that is actually helping to push or pull the toboggan in the horizontal direction. So not surprisingly, you lose some of that in having this angle exerted. Now notice how this is cosine. Where does cosine attain its maximum value? So tell me where cosine attains its maximum value. There you go, at 0, because cos of 0 is equal to 1. That's its maximum value. So not surprisingly, where would I get the most bang for my buck horizontally is if the angle is 0, meaning if I'm pulling this toboggan in the same direction as the ground. Okay, and when it comes to Newtonian physics, what's nice about Newtonian physics is that the math sort of has to correspond with what's instinctively true, I guess. Okay, kind of that goes away a little bit with relativistic physics. Okay, so we expect that you get the biggest bang for your buck when you're just pulling in the same direction as the motion. All right. So let's take a look at number 4 here. Okay, so this one here, maybe we'll draw the diagram, because what's important this one here is to make sure we understand which vector is which. Okay, so if we look at number 4 here, okay, it says Horaceville is located 800 meters directly north of Horacestown. So here's Horacestown. There's Horaceville directly north. So I'm drawing my situational diagram here, at least to start off. All right. It says the wind is blowing from the southwest. So from the southwest, from here, meaning it's going northeast. Now again, we haven't necessarily said that, but it makes sense that if I'm doing northeast, it's right in between. Okay, when there's no angle specified, it's right in between. So this would be 45 degrees. Okay. And it tells us that the flight should last 4 hours. At what air velocity should the airplane be traveling? Okay. So remember what we want the plane to do. We want the plane to go from Horacestown to Horaceville. Okay. And this is often the mistake that's made, is that this is our ground velocity, our resultant velocity. This is what we want the plane to actually do. Okay, now how do I calculate this resultant velocity? Well, by taking the wind velocity and the velocity that the pilot will fly the plane at, okay, or the air velocity. So this here is our resultant velocity. This is what we want to be the end result. And how do I get to that end result? By adding the wind velocity, and then to that, I'm going to add the air velocity. So this is the velocity that the plane's pilot flies at. This is the wind velocity, and together they're going to sum up to this ground velocity. Okay, and of course this is 45, so this is 45. Okay, and we know that the magnitude here is equal to 60. Okay, is there other information that we have that's going to be useful to us here that we can add to this diagram? It's not given to us directly. There you go. Is we know that it has to travel 800 kilometers in 4 hours. So even though it's not specifically told, we'll assume that the velocity is constant. So the magnitude of this velocity is just 800 divided by, what is it, 4? So 200 kilometers an hour. Okay, and now I have enough information to solve this problem. Let's take a look here. Okay, so here's my diagram. Okay, and so I've got these two side lengths and an angle, so I can calculate the magnitude of the air velocity. Okay, and of course, because I'm working with one angle and two side lengths, I use the cosine law to solve for the angle. And if I want to give the direction, well, here I draw my little parallel line here. So if this is 45 and this was 119.9, I just subtract to get this angle here. Okay. So unfortunately, we're running out of time. So we'll just take a quick look at this last one. Okay. So this is an interesting one here because you've got a box that's on a ramp. Okay, so presumably it wants to move downwards. Now you'll notice here this is math, so we're just going to assume there's no friction, of course. Okay, but the only force that's acting on this object is the force due to gravity moving downwards. Okay, but what I'm interested in is what component of that force is going to move it down the ramp. So this is an example where we want to split this force vector into two perpendicular vectors, but not horizontal and vertical. Because I'm not interested in vertical or horizontal motion, I'm interested in the motion down the ramp. And so this is the component of that force that I'm looking for. So I can break it up into this force down the ramp and then perpendicular to the ramp. But hey, look what I've got. Nice right angle triangle. Question is what information do I know? So I know the magnitude of the force because they give me the mass, okay? But I need an angle. And here down below is where I do a little bit of old-fashioned geometry, and I'm given the angle of the ramp. And you see that I'm creating these two right angle triangles. This is the right angle triangle of from my force components. And then I just draw a straight line here to create a second right angle triangle. And what I'm able to do is realize that this angle is common to both triangles. So I use this right angle, knowing this is 20, meaning that that's 70. But now look what I have. I have an angle inside the triangle that I'm trying to solve. Okay, so in this case here, I'm looking for this force down the ramp. I can use cosine. But if I want to stop the box from sliding down, I have to apply the force in the opposite direction. In other words, I'm looking for the equilibrium force. What would I have to push? I'd have to push at a force of 670.36, but going in the direction up the ramp. Okay. So the work is posted. Send me, there's already one video, I think there's one video that's already posted, maybe a couple of others that I posted preemptively.